Imagine you're trying to teach a teenager how to drive, right? But instead of ever putting them behind the wheel of an actual car,
Yeah.
you just force them to watch like a million blurry, shaky TikToks of car crashes.
Oh, wow. Yeah, that sounds like a terrible idea.
Right. It's a disaster. But that is exactly what autonomous vehicle engineers are accidentally trying to do today.
Yeah, quite literally.
So welcome to AI Paperslop, the YouTube series where we break down the most dense, critical tech papers specifically for you, the ML engineers and the researchers who are actually building these systems.
Because there's a lot of slop out there to sift through.
Oh, definitely. And today, we're tearing into this massive paper. It's called Sensor2Sensor, Cross-Embodiment Sensor Conversion for Autonomous Driving. It's this huge collaboration from researchers at Waymo, Johns Hopkins, Google DeepMind, and the University of Washington.
Heavy hitters.
Yeah, completely. And we are jumping straight into the core insight here. Basically, autonomous vehicles desperately need training data on what we call long-tail edge cases.
Right, the weird stuff.
Yes, exactly. Bizarre pileups, freak weather, pedestrians doing completely unhinged things. The catch is, your expensive AV fleet is rarely going to encounter these statistically rare events organically.
No, I mean, you could drive for years and never see a couch fall off a truck on the highway.
Exactly. Meanwhile, the internet has millions of dashcam videos of these exact scenarios. But an AV can't just, ingest a 2D YouTube video.
Yeah.
Its brain expects a 3D multimodal input. It wants like an 8-camera, 360-degree view perfectly synced with LiDAR.
Which a random dashcam definitely does not have.
Exactly. So this paper introduces a generative paradigm using 4D Gaussian Splatting and Diffusion models to magically convert a standard noisy 2D dashcam video into a full high-fidelity AV sensor log. And it's tailor-made for a target vehicle's exact hardware setup.
It really is, it's a watershed moment for robotics validation, honestly.
You think it's that big?
Oh, absolutely. The industry has been walled off from the largest repository of driving data in human history, which is the internet, simply because of, formatting and physics constraints.
Right.
What they've built here is a translational bridge, between unstructured, messy human data and the highly rigid, safety-critical data requirements of a multi-million-dollar autonomous stack.
So our mission for this deep dive is to figure out exactly how Waymo and DeepMind solved this massive domain gap without having, perfectly paired training data sitting around.
Because they definitely didn't have that.
Right. We're going to explore their incredibly clever latent representations, how they utilized a robotics concept called Dagger to fix temporal drift.
That part's so cool.
So cool, yeah. And how they managed to actually hallucinate complex LiDAR sweeps from a single uncalibrated dirt-cheap camera lens.
Yeah. To understand why the solution is so necessary in the first place, we have to look at the massive headache that is the autonomous driving systems, or ADS validation pipeline.
It's a total mess right now, right?
It is. Right now, there is a huge push toward generalist AI policies trained on massive aggregated data sets. But for safety-critical systems, per-embodiment evaluation is strictly non-negotiable.
Meaning you have to test it on the exact car it's going into.
Precisely. You absolutely cannot deploy a self-driving car without rigorously testing its specific, unique hardware layout in simulation first.
Okay, let's unpack this for a second. Imagine you're trying to train a world-class concert pianist.
Okay, I like this.
Right. So they know music theory perfectly in their head. But instead of letting them sit at a grand piano to practice the actual physical mechanics, you hand them a cheap toy keyboard and a staticky audio recording of someone humming a tune.
Yeah, they're not going to play very well.
No. The AV brain expects multidimensional geometry, precise distances, velocity vectors. If you feed its perception stack a blurry 2D video of a crash from a forward-facing lens, it has literally no idea what the distance to the car on the left is.
Or what's happening behind it, for that matter.
Exactly. The data formats are fundamentally incompatible.
And this incompatibility is what drives that long-tail data scarcity problem we mentioned. Collecting rare edge cases by just driving your AV fleet around in circles for millions of miles is, frankly, economically ruinous.
Right, because statistically, most driving is just boring.
Exactly. So the industry has desperately chased two alternatives, right? And both of them hit a brick wall when it comes to rigorous safety validation.
Yeah, so the first wall is with de novo scenario synthesis, which is, the realm of those generative world models everyone is talking about right now, like Waves GAIA1 or NVIDIA Cosmos.
Where you just type in a prompt and it generates a video of a driving scenario.
Yeah, exactly.
And look, those models are visually stunning, but they suffer from a massive plausibility gap.
What do you mean by plausibility gap?
Well, because they're generating the world from scratch based on statistical probabilities, the actual physics often break down under the hood.
Oh, like cars clipping into each other.
Exactly. Cars might subtly clip through each other, or shadows fall at like mathematically impossible angles.
Yeah.
Or the momentum of a crash just straight up ignores Newton's laws.
Right, so for a human watching on Twitter, it looks fine.
Yeah, it looks great to us, but when you feed that data into a rigid AV perception stack, the system flags it as impossible immediately. It just knows it's hallucinated data.
Which naturally leads engineers to the second alternative, right? Scraping the internet, grabbing real, in-the-wild third-party data from Nexar dashcams, VOFOs, or just smartphones taped to windshields.
And that absolutely solves the plausibility gap, because the video is of the real world, the physics are inherently perfect.
Right.
But that introduces the embodiment gap. You're dealing with a single monocular video. It's completely uncalibrated.
Right, like you have no idea what the focal length of the lens even was.
None. It lacks 360-degree coverage, and obviously there are no lasers strapped to the hood of that random Toyota Camry in the video.
So wait, why couldn't they just throw a massive image-to-image translation network at this? I mean, we have models that can turn a photo of a horse into a zebra. Why not turn a dashcam frame into an 8-camera Waymo frame?
Because classical unpaired translation methods fail catastrophically here. They lack strong geometric priors.
Geometric priors.
Yeah, basically an understanding of 3D space. A standard GN or diffusion model might learn to make a dashcam video look like it has the color grading of a Waymo camera, sure.
Okay.
But it can't mathematically infer a 360-degree 3D world, including the exact depth of every single object behind the camera from a flat, forward-facing 2D plane.
Ah, meaning Sensor2Sensor has to actually learn the underlying geometry of the world.
Exactly.
But that brings up a massive paradox, doesn't it? To train a model to translate a 2D dashcam into a full 3D AV log, you need perfectly paired training data.
You do.
You need the exact same car crash recorded by a $40 dashcam and a $100,000 Waymo rig at the exact same millisecond. Since you obviously can't, like, time travel and strap a sensor suite onto a random car in a 2015 YouTube video,
Okay.
how do they build a data set to train this thing?
Okay, so they executed this brilliant data curation pipeline that acts as sort of a reverse synthetic hack.
A reverse hack? How so?
Instead of trying to find dashcam footage and upgrade it, they started with the pristine data they already owned. They took about 100,000 scenes of real high-fidelity AV logs, featuring their full 360-degree camera arrays and LiDAR point clouds.
Okay, scenes that were about 10 seconds each, right?
Yep, 10-second clips. And here is where they brought in 4D Gaussian splatting.
Oh man, Gaussian splatting. For those deep in the rendering weeds, this represents a 3D scene using millions of mathematical splats of color, opacity, and scale.
Right, but they use the 4D variant, which accounts for time.
So it's not just a frozen statue.
Exactly. They didn't just build a static diorama. They specifically supported dynamic rigid objects, so tracking other vehicles moving through the scene, and deformable objects.
Deformable meaning like pedestrians walking.
Exactly, capturing pedestrians moving their arms and legs. And they accumulated these splats into what's called a canonical object model.
Right, separating the moving stuff from the static background.
The canonical object model is crucial there. By separating the moving objects, they could accumulate observations of a car across multiple frames. Even if the AV only saw the front of a passing car in frame 1 and the side of it in frame 10, the canonical model stitches that into a complete 3D representation of the vehicle over time.
Okay, so they have these perfect, playable 4D digital twins of real driving events.
Right.
Then what do they do with them?
They placed virtual dash cams inside these 4D scenes.
Oh.
Yeah, they basically told the rendering engine, pretend there's a cheap camera sitting right here inside the digital scene, and rendered synthetic views from that specific spot.
Wow. Suddenly they solved the paradox. They have perfectly paired training data now. A synthetic dashcam video perfectly synchronized with the real ground truth AV log.
Yes.
But we have to push back on that a bit, though.
Go.
3D and 4D Gaussian splatting are purely reconstructive technologies. They do not hallucinate geometry well at all. So if you place that virtual dash cam way outside the original flight path of the Waymo cameras, doesn't the rendering quality just drop off a cliff?
Yeah.
Like, wouldn't you just get a warped, smeared mess?
You absolutely would, and that is a fundamental limitation of splatting. But consider the physical reality of the problem they're solving.
Okay.
A dashcam mounted inside a car is still generally within the same spatial bounding box as an AV's main sensor pod.
Oh, that's true. It's on a car.
Right. It might be a meter lower on the windshield or shifted slightly to the driver's side, but you aren't trying to render a view from the Goodyear blimp.
Okay, fair point.
The virtual camera is close enough to the original poses that the reconstruction holds up quite well. But to your point, it isn't perfect, and they actually use that imperfection to their advantage.
Right, they had to make sure the model didn't overfit to pristine simulations, so they heavily degraded the virtual camera feeds.
Heavily degraded them.
How did they actually simulate garbage data, though? Did they just slap like a Gaussian blur filter on it?
Far more sophisticated than that. They mathematically sampled intrinsic camera parameters to ruin the image.
Okay, ruining it with math.
Exactly. They injected random noise into the focal length, like plus or minus 5% noise. They shifted the principal points and tweaked the distortion coefficients to mimic that awful fisheye warping you get on cheap ultra-wide lenses.
And they messed with the physical placement, too, right? The
Why?
extrinsic parameters.
Yep. They sampled 6 degrees of freedom poses, simulating mounting the camera on different vehicle heights, like a low sedan at maybe 1.1 meters versus a taller SUV.
Oh, and they even introduced rotational perturbations like pitch, yaw, and roll, right?
Yeah.
Just to simulate a dash cam that a driver just slapped onto their windshield slightly crooked.
Exactly. And what's fascinating here is the underlying philosophy of this approach.
Yeah.
It turns the entire generation process into a denoising task.
Ah, I see.
Because the synthetic dashcam input has all these distortions, plus minor reconstruction artifacts from the splatting process itself, the neural network isn't just learning a simple style transfer.
It has to actually figure out what the image means.
Right. By forcing the network to map these degraded, distorted inputs back to the pristine ground truth AV data, it is forced to learn robust spatial and semantic mappings. It has to actually understand that a warped smear of pixels is a car and accurately place it in 3D space.
Okay, so they completely solved the data problem. They have a massive paired data set. Now they need the architecture that performs this massive cross-embodiment conversion.
And this is where it gets heavy.
Yeah, because hallucinating 8 cameras to get a 360-degree view from a single front-facing lens is already an incredible leap. But we need to talk about hallucinating lasers. How on earth do you generate highly precise LiDAR sweeps from a 2D image?
They built a conditional diffusion model using a multi-stream U-net backbone.
Multi-stream meaning they split it up.
Yes. Rather than processing everything in one massive clump, they have separate processing streams for the camera data and the LiDAR data. These streams talk to each other through shared cross-attention layers.
So they stay synced.
Right. This is vital because the model needs to learn the specific physics of a camera lens independently from the physics of a laser pulse, while still ensuring that if a car appears in the camera stream, it appears in the exact same physical space in the LiDAR stream.
Here's where it gets really interesting. If you work with raw 3D point clouds, you know they are an absolute nightmare for diffusion models computationally.
Oh, absolutely unmanageable.
It's just too much sparse, unstructured data. So the researchers didn't use raw point clouds at all. They mapped the LiDAR to a 2D range view spin image.
It is an incredibly elegant compression technique. They created a 2D image where the rows map to the sensor's elevation angle, so how high or low the laser fired, and the columns map to the azimuth angle.
The 360-degree rotation of the sensor.
Exactly.
And they set the depth dimension of this image to just 4 channels. Instead of red, green, and blue, you have 4 highly specific layers of data.
Right, so let's break those down.
Yeah, layer 1 is range, the physical depth in meters, which they clamp at 150 meters and scale between 0 and 1 just to keep the math clean.
Yeah.
Layer 2 is intensity, essentially how bright the laser reflection was. And layer 3 is elongation.
And elongation is a brilliant inclusion here.
Yeah, explain that one.
It describes the extent to which the returning laser waveform was stretched or flattened when it hit a surface.
Okay, so like materials matter.
Completely. A laser hitting a perpendicular metal license plate returns a very sharp, quick pulse. But a laser hitting the curved, muddy rubber of a tire returns a stretched, elongated pulse.
Oh, wow. So it gives the model subtle clues about the angle and material of the object.
Exactly.
And that final 4th layer is just validity, a binary mask of ones and zers, indicating if the laser actually returned a signal or if it just shot off into the empty sky. Compressing massive, chaotic 3D point clouds into a 4-channel 2D image is just genius. It allows them to leverage the existing, highly optimized power of standard 2D image diffusion models instead of trying to invent a completely new diffusion process for 3D space.
To pull this off, they designed a specific LiDAR variational autoencoder, or VAE, and the loss functions they use to train it are meticulously tailored to the physics of LiDAR.
So what are the losses?
They use standard L1 loss for the continuous variables, so range, intensity, and elongation. They use binary cross-entropy for that validity mask we talked about, but the real secret sauce is how they handle the geometry.
The LPIPS loss applied to the surface normals, right?
Yes.
Now, wait a second. LPIPS is a perceptual loss metric. We usually use it in image generation to make sure a generated face actually looks like a human face to the human eye, rather than just mathematically matching pixel colors. How and why are they using an image perceptual loss on invisible 3D geometry?
It sounds weird, I know. But they compute the surface normals, the directional angles of the surfaces in the scene, using finite differences from the projected 3D points.
Okay.
By enforcing an LPIPS loss on those normals, they are forcing the neural network to actually care about the structural integrity of the generated geometry.
Oh, I see. So without it, the model might get the general depth of a wall right, but the points would be a jagged, noisy mess.
Exactly. The LPIPS loss on the normals ensures that a flat wall actually looks mathematically flat and structurally coherent. It forces the hallucinated LiDAR to behave like physical objects in the real world, not just like a cloud of floating static.
That makes total sense.
Okay.
So we've successfully generated a perfect single frame of 360-degree video and a full structurally sound LiDAR sweep from a cheap dashcam image. That alone is a paper-worthy achievement.
Completely.
But driving isn't a photograph. It happens in continuous time. And anyone who has played with open-source video diffusion models knows the compounding error problem.
Oh, the temporal drift. It's brutal.
Right. Frame 1 looks photorealistic. Frame 2 is a little soft. By frame 10, the cars look like melting Salvador Dali paintings, and the lane lines are doing loops. How do they keep this hallucination temporally consistent across the whole video?
Well, they utilize an autoregressive modeling approach. The model doesn't just guess the next frame in isolation. It predicts the next frame conditioned on the history of the previous frames.
Right, but that doesn't fully fix the compounding error, does it?
No, it doesn't. But to actually solve that compounding error drift you mentioned, they pull a technique straight out of robotics called dagger.
Wait, isn't dagger an imitation learning concept? I've seen it used to train robot arms, not generative video models.
It is. Dagger, or dataset aggregation, was introduced back in 2011 to solve cascading failures in robotics.
Right, like if a robot makes a tiny mistake.
Exactly. If you train a robot purely on perfect human demonstrations, the first time the robot makes a tiny millimeter mistake, it enters a state it has never seen in its training data.
And panics.
It panics, makes the worst mistake, and the errors cascade until the robot drops whatever it's holding. Dagger solves this by having an expert correct the robot's mistakes during training and aggregating those corrected recovery paths back into the dataset.
Wow, so they ported a reinforcement learning policy correction concept into a diffusion model. That is a wild architectural crossover.
It really is.
The training pipeline for this is a 4-step process, right?
Mm-hmm.
Step 1 is just base conditioning, training it to generate single frames. Step 2 is previous frame conditioning, feeding it the immediate past frame so it starts to understand short-term motion vectors.
Yep. And step 3 is the crucial dagger data generation phase. They take that model and they unroll it for a 6-step rollout.
What does that mean in practice?
They force the model to autonomously generate its own sequence of 6 frames without any hand-holding. Because it's an imperfect generative model, it naturally starts to drift.
The Salvador Dali effect.
Right. The cars might start to warp. The LiDAR might get noisy. This intentionally creates a degraded data set full of compounding errors.
And then step 4, dagger fine-tuning. They take the model and train it on its own degraded outputs.
Exactly.
During training, they randomly swap out the perfect ground truth history with these hallucinated drifty frames, but force it to predict the correct perfect next frame anyway.
If we connect this to the bigger picture, it's a profoundly elegant solution. By forcing the diffusion model to look at its own accumulating errors, it learns the path back to reality.
It learns to recover.
Right. It learns how to recover from a bad hallucination. It stops the compounding error cascade dead in its tracks, resulting in a temporally locked, highly consistent video and LiDAR sequence that stretches smoothly across time.
That is just brilliant engineering. All right, let's bring all of these highly technical pieces together. What happens when you unleash Sensor2Sensor out in the real world?
The capability demonstrated here is that you can take a highly compressed, noisy video from a random consumer dashcam, or literally just a smartphone taped to a dashboard, and Sensor2Sensor can reliably spin up a usable, temporally consistent, multimodal autonomous vehicle log.
We're talking 8 high-resolution camera views and a full 3D LiDAR point cloud, completely synchronized in space and time, generated from a single 2D lens.
It's unbelievable.
The value proposition for companies like Waymo or anybody building AV stacks is staggering. We can finally unlock the vast scale of in-the-wild internet video.
Which is endless.
Endless. Every bizarre crash, every freak snowstorm, every weird edge case ever caught on tape by a random driver can now be safely piped directly into simulation pipelines to validate software against the absolute rarest scenarios.
It effectively obliterates the boundary between unstructured human data collection and structured robotic data ingestion. You no longer have to wait for your $200,000 sensor pod to witness a rare event. You just download a clip from YouTube and translate it.
So what does this all mean for the future of the hardware itself? We've covered how they reverse engineer the data with splatting, how they elegantly compressed LiDAR into 2D channels, and how they fixed temporal drift with Dagger. But I want to leave you with a bit of a brain bender built on the actual mechanics of this paper.
Let's hear it.
If this conditional diffusion model is getting so insanely good at hallucinating perfect 3D geometry, precise LiDAR point clouds, and comprehensive 360-degree views from just a single, cheap 2D dashcam input, does the target vehicle even need a $10,000 physical LiDAR rig and 8 cameras at inference time in the future?
Oh, wow.
Right. Like, could an optimized descendant of Sensor2Sensor eventually evolve from being a back-end training data generator into a real-time software sense?
Running live in the car.
Exactly. Could it run live right inside the car, generating real-time 3D environments from a single cheap lens and replacing the expensive physical hardware entirely?
That would change everything.
Something for you to ponder before your next compile finishes. Catch you next time.